We are here on the last earmark subject area under the business mathematics and statistics. Uh, this is on the selected financial applications. We are hoping to discuss three important areas. We'll start with the today's lecture, that is on the present value of uh, future cash flows, net present value, and time value of money concept is stemming from all these instances. And then we will move on to treasury bond and treasury bill pricing. Those are the government security pricing related area. That is also one important aspect which you can focus. If you categorically look at the recent examinations, you can find ample number of questions, mainly one or two MCQs, as well as at least one complete 20-mark question. So that is also an important area. And then we'll wrap up our discussion on this last segment, that is on the portfolio theory, where we will be summing up all the knowledge that we have gained so far on the financial asset classes. We will learn to calculate the returns, calculate the portfolio returns, portfolio risks aspects as well. And then that will be the end of this selected lesson on uh, area number 9. Thereafter, we'll hoping to go through one or two revision sessions, as well as we will try to continue the momentum with the question and answer through the online questions that we're sharing in the portal. Okay. So having said that, we will start with the today's lecture, that is on the time value of money. Okay. Okay. So this is one important syllabus area under the business mathematics, where you will be invited to look into the cash flows of different projects, different asset classes, and mainly you will be in a position to understand the differences between the timing of these cash flows, as well as the occurrences, as well as some patterns like continuous cash flows up until a certain time period, and a certain time period till infinity, certain times till a defined number of intervals, so on and so forth. So this concept is one of the oldest concepts in the finance, and I would say one of the fundamental or building blocks into what you are learning in your advanced finance subject. Especially, you will learn more on this subject area under your financial management subject area in the next level of the IBSL curriculum. Having said that, this is the expected content to be covered on the today's content. Uh, we'll first look into the future value. Uh, Presently, there will be certain values for a cash flow given, but first we will try to understand what would be the current value of today's money worth in a future time period. And there, of course, we will come to the next area on the present value, where you will understand that is nothing but the opposite of the future value, where you can compare today's position with a future set of given cash flows. Okay. When we discuss the future value and present value, of course, the two important areas that we are going to further deliberate is one on the compounding. The simple interest as well as the compounding interest are the foundation of some of the equations that we are going to discuss under today's area, that is on the future value and the present value. And area number 4 and 5, that is on the nominal and effective interest rate and the annuities, and there's an extension of the annuities, that is the perpetuities. Those are, of course, some of the practical instances that we can see future value and present value are being used in our day-to-day investments. It may be a fixed deposit, maybe a small project. You can understand how the effects of effective rate and annuities and perpetuities comes into play. Lastly, we will discuss on the net present value and IRR. Of course, if you look at this entire section, area number 7 is the key focus of the lecture, where you will understand how to calculate the net present value of a given set of cash flows. So once you will have a set of cash flows for a project, of course, you will understand that you can't compare those cash flows unless you compare them in a constant time period. So the next concept that is stemming from the net present value is nothing but the IRR, where you will learn for a project or for a set of cash flows to sort of like a break even, what would be the rate that we need to invest, or what would be the rate that we should return in order to the initial cash outlay to be balanced with the rest of the cash flows. So this is the outline of what we are going to learn under the session on the time value of money and some of the basic corporate financial concepts. We'll move on. It's an interesting session. Hopefully, we will spend the entire day on discussing the theoretical areas, and probably we can spend the next week to cover up some of the most recent exam questions, as well as some more interesting theoretical areas. Okay. Okay. So first, this is the most important concept that we are going to discuss today, that is on the blue color. The people would prefer to have money at present than in a future date. So the entire discussion on the net present value, as well as the areas on say perpetuities, annuities, effective interest rates, the NPVs, the IRRs, and everything boils down to this point on the highlighted blue color text, that is the people would prefer to have money at present than in a future date. So the time value of money is a concept that has been built based on this particular concept, such that always people want money in advance compared to they want the money in a future date. Why do we say like that? Say you have two options, either to receive 1,000 rupees now, or you have an option to receive 1,000 rupees in 7 months time period. So when you look at a period ahead of 7 months, there would be a lot of uncertainty. Your cash flow will have a different valuation at that point. And if you have 1,000 rupees now, you can do something with that 1,000 rupees. Maybe you can put up a fixed deposit and earn some interest. Maybe you can, put it into an investment. Maybe you can, buy some small amount of, let's say, consumables, and then you sell it at a profit, and then make maybe 10 or 20% return. So that is all if you have that 1,000 rupees now. But what if you have that 1,000 rupees in 7 months time period? There, of course, you will have to have something in return to compensate that 7 month time period. So the time value of money concept says, if you want money now than in a future date, there has to be something in between these two factors, that is money worth now versus money you are getting in a future date. That is nothing but the cost of money, or the interest, which I've highlighted in point number 3 here. That is the birth of those two instances. So I missed the second part. Provided all other factors remain same, concept of time value of money depicts that people always prefer to have money now than in a future date. But we'll discuss what are these factors in a moment. Okay. Third point says 100 rupees at present is not going to worth 100 rupees in a future date, where it arises the concept of cost of money or interest. Now in our class example, we discussed that if you have 1,000 rupees now, you can do a lot of things till you get the 1,000 rupee in 7 months time. So your 2 points to compare this entire discussion would be 1,000 rupees now versus you're getting 1,000 rupees in a future date. So if you discuss the first option, that is you have money right now, the choice is you can spend that money and get a return. So if you want to compare that 1,000 rupee with the 1,000 rupee that you're going to get in 7 months time, obviously the missing factor is the term that we name as the interest, where you need to pay the person who is getting 1,000 rupees in 7 months time some additional money in order to compensate the foregone opportunity, or that is what we call as the cost of money. So lastly, I would highlight the fact that the time value of money concept suggests that cash flow should always be compared based on their present values and not the individual future values at different time periods. Why do we do that? That is in order to portray a fair comparison. Let's say mathematically, you can add up a couple of numbers, 100, 200, and 300, and you can say the total is 600. But can you add 100 rupees now, 200 rupees in 1 year time, and 300 rupees in 2 years time? You can add it together and say 600, but financially, mathematically, it would be somewhat wrong to do that. Rather, you can start with that 100 rupee now. That's not a problem. But the 200 rupee that you're getting in 1 year time should be compared to a number that is in order to add it to the original 100, which is now. And the 300 rupee, next 300 rupee that you're getting at year 2 should be also adjusted with a different factor to make sure that you compare that 100 rupee in a similar time period. That's the important last point we want to touch upon from the time value of money. If you want to compare the cash flows at different time period, you can't merely add them or deduct them. Rather, you have to do a financial adjustment, or rather financial mathematical adjustment, to make sure that you are doing a fair comparison. Let's move on. So the factors that we discussed on the class example of 1000 rupees now versus 1000 rupees in 7 months time, the time value of money suggests that those two are going to differ from each other. That 1000 rupee at 7 months time is a different number from the 1000 rupee now, which could be summarized in some of these factors. The first one is that we always prefer to consume now rather than in an advance period. Let's say if you don't even consume, that's okay. You can keep that money in a safe place, and then you can get that money at your disposal rather waiting till 7 months to get the 1000 rupee. Second point, the inflation will decrease the money value. So the concept of inflation says that eventually, as economies grows, the goods and services will gradually have a increasing effect on a price. So there's a negative inflation in some economies, which is a opposite discussion. Rather, in typical terms, inflation suggests that always goods and services are going to have a higher value in a upcoming time period than now. That is why merely if you look at factors like salaries, salary adjustments, pay adjustments, and all are happening. Why? Because at a decent inflation rate, we have to expect that prices will tend to go up. So the time value of money concept always suggested that if you have to compare two different price points, inflation effect will also have to be compensated. Third point, uncertainty ahead of the future. Say now if you get the 1000 rupee now, you're happy, but if you want to get the 1000 rupee in 7 months time, you have to wait till approximately 210 days. So 30 days into 7 to 10. So within 210 days, a lot of things can happen. Your domicile's economy may have an impact due to some unavoidable circumstances. So maybe an outbreak like COVID-19 can kicks in. Maybe you can get sick. Maybe you may lose your job. You may have some negative impact on your businesses. A lot of things can happen. So always when there's uncertainty ahead in the future, the time value of money suggests that your money in future cannot be compared with the money right now. The last and the least point that we want to discuss is the cost of money. That is a opportunity cost that we discussed a moment ago. If you have your money at your disposal right now, you can always invest that money and get a return, so that it will be a bigger number in 7 months time in our class example. So all these factors you prefer to consider now, the inflation effect, uncertainty, opportunity cost. So everything, these are sort of like variables for this dependent variable of y, that is a time value of money, to have a different valuation for the cash flows in a future date. So the argument again I want to stress is the time value of money again and again suggests that uh, timing difference of cash flows is going to make problematic situations where we need to find a mechanism to compare the different time periods cash flows in a similar ground, so we can add them, deduct them, take the summation and say which is going to give me a positive cash flow, which is going to take money or take wealth away from me, and do a lot of comparisons. So coming from the time value of money concept, now we are going to discuss the important section, that is on the future value. Okay, we discussed that interest is going to be the cost of money, and in some other instances also we discussed that cost of money or the opportunity cost is going to cost the future cash flows somewhat higher than the present cash flows worth somewhat higher than the future cash flows. So the future value concept suggests that, let's say, if you look at this simple timeline example, I have put year 0 here, that is the current point, year 1 here, and this 10% suggests that we are going to get some interest for this time period for whatever the money, whatever the amount that we are going to invest. So the term future value can be defined as, that is a value in monetary terms of which we are going to see a growth at a specified rate for a specified time period. Now in this example, I say it is 10% for 1 year time period. And let's say we have a notional value of 100 here. That means after 1 year, we should see a value of 110. If I simplify that terms, the FP stands for future value, PV stands for present value, and R stands for that interest for the particular time period, we can always say the future value that we are going to observe after the time period is going to be the summation of present value, that is a current value, plus the interest as a percentage that you are going to get to compensate what you are losing right now. So in some simple terms, if we try to multiply this bracket and look into these two terms in an independent way, what we see is this is PV into 1, that is the present value, and this is PV multiplied by R%, that is the interest rate. Let's see a simple example of 100 rupees. Consider an investment of rupees 100 with an interest 10%. We discussed a moment ago what is the future value. So the future value, as suggested by the previous equation of 1 plus R multiplied by PV, we have the present value, that is a 100 rupee, multiplied by 1 plus 0.10 in decimal terms. In percentage terms, you can say 1 plus 10% also. So eventually we can see the future value of this 100 rupee after 1 year is going to be 110. So the 110 comprises of the principal value of 100 and the interest of 10. So these are the two components. This 100 and the 10 are the two components of what you can see inside the 110. So this process of multiplying the present value by 1 plus interest is also known as simple interest. So the term simple interest suggests that you have a value right now, you multiply that by R% or T% or Q%, and then you're going to get your face value, let's say 100 rupees, that is your present value that you see right now, multiplied by the percentage, in this example 10%. Now, this is a simple example of we receiving 10% for a single time period. But what if we receive the interest for multiple time periods ahead? Now, this is the last point that we're going to stress here. When we receive interest for more than one time period, concept of compounding is going to deliver an answer. So the compounding concept, which is the concept that is coming from uh, you're going to add more than one item to the previous item. So the concept of compounding is the extension of the simple interest calculation method, or sometimes we can call it as a compounding interest calculation, where you're going to assume that you're going to get some intermediate payment, and then your value at the last is going to get grown at a somewhat exponential rate compared to the simple interest rate that you can simply multiply. We will see what the compounding interest rate is going to tell us. Now look into this example. We had a initial investment of 100 rupees with an interest of 10%. Now this 100 rupees, instead of just multiplying that by 10% and getting 110 after year one, instead of that, this 100 rupee is going to invest for a period of more than 1 year. If you look at these arrows, you can see this 100 rupee has moved from T0 to T1 to T2 to T3. So we'll see the future value of this 100 rupee after these particular intervals. So the first calculation we already discussed. After year one, the value of the current 100 is going to be 110. So the second point, the important point is at year two, you're going to start with not 100 anymore, rather 110. So when you start with 110, and then when you grow at 10%, obviously you're going to get a little more than 10 rupees this time. So previously you got 10 rupees here, but now instead of let's say if you get another 10 rupee, the value here should be 120, isn't that so? So instead we see a gradual increase of 1 rupee compared to this simple point of the simple interest of 10% that you got here. So what has happened? Instead of you starting with 100, now you have received 10 rupee as an interest at the end of time period 1. So for that 10 rupee, that additional 10 rupee also, you're going to get another 10%. So what's the value of 10 rupee multiplied by 10%? That is 1 rupee. So if you try to decompose this 121, what you see here is you see the 100 rupee that has came from inception. That's fine. This 10 rupee that you have received for year one, that is also there. So for this 100, another 10 rupee that is also there. 100 plus 10 plus 10, you have to see 120. And the addition is this additional 10 rupee that you have received after year one is getting another 1 rupee of interest. So this 121 now has 4 components: 100, 10, another 10, and 1 rupee. So the compounding interest, that is the summary that we can observe. So any cash flow that you did start with has grown by certain interest amount, will also get more interest on another time period. Say you're going forward with the investment. So this is interest on interest effect is the summary that we can see when we look into multiple cash flows, or you're receiving interest over multiple time periods in a instance of an investment or another project cash flow or anything like that. So the last point, let's say at T3 also, we start with 121 and receive another 13.10 plus the 10 plus the 11 that you received here. Sorry, so then it has to be 12.10. Let me repeat. This 133 should comprise of the 100 that came in. Okay, that's fine. This 10 rupee. Okay, 110. This 11 rupee. That is that 21 minus 10. That's also fine. So that means 121. So 133 point. Sorry, 133.10 minus 121. Then you have received another 12.1 rupee of interest. That is the 1 rupee that you have grown so far is going to get another one, another 10 cents of interest. So it's a beautiful concept, isn't it? So the interest that you receive in a particular time period is going to get another interest for another time period ahead. So the effect of compounding is the basic foundation that we are going to lay for our next discussion. That is the generalization of this pattern of future cash flows. Okay. So if you look at uh, now, okay, before we move on, let me just try to visually discuss with you guys on the last 133.10. Okay. So you have the 100 here, 100 and sorry, 110 here, then we have 121 here, 133.10 here. If you try to decompose this 133, we have the 100 that came from here, that's fine. So we accumulated 10 rupees from here to here, 11 rupees from here to here, and then how much 12.1 from here to here. So this 10 rupee that you received here is going to also, and that 10 rupee is going to get more interest at this point. That is also going to come here. So this extra 10 rupee is going to have another interest. That sorry, this is going to be 10 rupee grown here, 110, grown at a rate of 10%, 121, grown at a rate of 12 point, another 10%, 12.1, that is 133.10. So the last point I want to stress upon is the 1 rupee that you get here is going to get another 10% of interest. That is the point that you see here. So you have 10 plus 11 plus 12 plus 0.1. I think I got it correct. Yes. The initial 100 is 10 rupee. This 11 rupee from here to here. This 12 rupee plus this 1 rupee that you got the additional from 110 to 121. That also at 10%, 0.10. So the summation of all this is the 133.10 that you see here. So every cash flow that you receive in between is going to give you more interest. So that's the argument we want to highlight. Okay, now let's say we want to generalize what we discussed so far on the compounding of interest into a universal equation. Now, instead of years, sometimes your cash flows will have different time periods. You can discuss monthly cash flows, weekly cash flows, daily cash flows. Even less than 1 day is also possible in some instances. If you categorically look at certain practical examples like calculating inflation in hyperinflation countries like Zimbabwe, I remember they used to publish inflation on less than 1 day time intervals also. So mathematically, your time period, your definition of time could be from it should be there are more equations to discuss under the future value and present value scenario compared to what we are discussing on n to be a perfect number. Sorry, the whole number of years. Theoretically, you can break down n into uh, an extreme milliseconds and microseconds, and it could go to the extreme level, which you can't really calculate. Then the concept of e, that is 2.78, that also comes into play of these equations, where you can break down the time period further. We won't go to that far in our discussion. Rather, we are considering, and we are going to consider only time periods of whole numbers like days and weeks and months and years. So the previous discussions we had so far suggested that provided you have yearly cash flows in a nicely way, 10%, you can calculate the interest that you're going to get from each time period, and we can move on. If you want to generalize what we discussed so far, this is the form of equation which is going to give you an answer for any number of time periods at any rate. If you break down our previous discussion on this 121 and 133.10, what we have eventually done is the interest that we are going to get from a certain cash flow, we have grown it by the interest that we are going to receive for that time period. That is 100 multiplied by 1 plus 10%. That extra 10 rupee multiplied by 1 plus 10 rupee. That extra 11 rupee multiplied by 1 plus 10 rupee. So any cash flow you can multiply and break it down and get an answer for a future value. So the future value equation is going to suggest that any given present value, if you multiply that by 1 plus interest rate times the number of time periods that you're going to get the interest period, easily you can get the future value at any time period. So the previous example that we discussed a moment ago had a present value or a starting value of 100. Okay, so instead now mathematically what we just did, we went to 110, then we went to 121, then we went to 133.10 as our answer for the future value after a time period of 3 years. But this equation suggests that what we have done could be mathematically sum it up to 1 plus r to the power n and easily calculate the future value at any time period. If you try to apply the same numbers, what you're going to get is this future value. Let me try to go to the board again. So this future value of 133.10 is going to come from 100, 1 plus 0.10 to the power how many time periods? 1, 2, and 3. So eventually what we have done here, 100 multiplied by 1.10, 1.10, and 1.10. 3 times. We get 110 here, we get 121 here, and 121 multiplied by 1.1 is going to give you this answer of 133.10. I'll try to break it down again. 100 into 1.1 is going to give you 110. 110 into 1.1 is going to give you 121. 121 into 1.1 is going to give you 133.10. So the equation that we can discuss as future value is going to be equal to present value 1 plus r to the power n is the building block, absolute building block of the discussion on the future value and present value and time value of money. So you have a present value of 100. You know your interest rate 10%. You know your time period as 3 years, and then you can calculate future value. But what have I done here? Here, instead of future value, I've taken present value into the equation's right hand side, and I've taken the 1 plus R2, the division of future value as shown here. So the concept of present value and future value are very related in a hand-in-hand way if you carefully look at the equation that I've shown here. Present value of a future cash flow. Let's say you know after 5 years time you are going to get 161 rupees. After 5 years time you are going to get 161 rupees. If you know that 161 value right now, that means the numerical value, okay? If you know after 5 years 161, and then you can use the same equation to calculate what it is worth right now by inverting this future value equation easily. So you start with a value, then you know what is going to be the end value if you use the equation as it is. But if you know the end value also, you can easily take that value and calculate the value of your end value as a today's term by just inverting the future value equation. Okay. So important point to note is the equation on red box here. Future value is equal to present value 1 plus r to the power n. So this is again, guys, is the absolute building block of the time value of money concept. Okay, we have to be carefully look into these terms in discussions we are going to have in a moment to how to distinguish this r and n. Look at the future value, present value. These are going to be numbers. Okay, that's perfectly fine. But what about this R and N? Now these are going to be the important points that you will see depending on your cash flow pattern. And I iterate the fact that this is where you're going to go wrong if you do not understand the interest paid for the particular time period and number of time period that you have your cash flows flowing in. Okay, don't worry, we'll see that in a moment. Further, if you look at the future value of a trending cash flow by looking at this equation, for the two variables of interest rate and the number of time period, if I take two axes like this, I've taken x-axis for the n or the number of time periods here, and I've taken the y-axis for the interest rate or to calculate the 1 plus interest rate to the power n. So this is the future value in the y-axis. What you could see is, you can see when you do the compounding, considering the reinvestment of the intermediate cash flows, higher the interest rate on one aspect, you're going to get the future value in a much more higher way. And also higher the interest rate on one aspect and higher the number of time periods that you're going to do this compounding, your future value is again going to increase rapidly. If you look into these graphs carefully, what you can see here is this blue color line is the interest that you're going to get at 2% and at different compounding frequencies of 1, 2, 3, so on and so forth. So this is the growth of that 1 rupee after 10 time periods grown at 2%. So it's going to be somewhat around 1.2 or 1.3. When we move the interest rate from 2 to 4, what you can see is your future value after 10 time periods is going to be much higher, close to 1.5. The light blue color, 6%, even higher. Now we are close to 2. Where the yellow color, that is 8%. So this interest rate now is 8%, and you're comparing this everything at 10th cash flow. At yellow line, what you see here is 2.1 or 2.2 is your 1 rupee value after 10 time periods. 10% even higher, 12% even higher. So this simple chart is going to tell us a story that when you see the value of R and N into higher territories, obviously your future value is going to be higher. And if you see the movements of R and N at lower phases, like here, you could see a smaller growth in the future value. So we have to understand the value of R and N in order to get an understanding of a comparison, provided you have given multiple choices. A good example would be you can walk into a bank and ask for a different propositions or different opportunities to invest your fixed deposit money. You will see different N's and you will see different R's, and accordingly you can calculate your future value and see what you are going to get at the end of your investment. So in practical sense also, R and N is going to be get vital, and obviously your N's, the number of frequencies of the compounding interest that you're going to get, will be controlled by the bank in order to make sure that one option is not going to give a significant advantage over the other investments. So depending on your need, if you need intermediate cash flows, if you need, let's say, uh, uh, if you don't need intermediate cash flows, rather you need one cash flow at, let's say, after 5 years or 10 years. So your N's and R's can make sure that you get a similar benefit at the year end, not much advantages to one or two options. So practically, your interest rates that you can see in a bank will be a derivation of a nice yield curve that has been built upon the risk-free rates. And depending on the interest rate climate, the banks will obviously change the uh, R, the interest rate, and accordingly for different ends, so different time periods, you can get different returns. So it's this graph is going to tell us that story of higher the interest rate and higher the number of time periods that you're going to compound, obviously your future value is going to get higher. Okay, now this is the extension of what we discussed so far on the R and M, provided that we are going to get intermediate cash flows for a time period. Okay, now these terms N's and M's is maybe somewhat confusing at once, but carefully look at what we are going to discuss here. For a time period of capital T equals simple N. Now our time period is N. So N, 2N, 3N, 4N is going to be the timing of your next interval. Let's say N is 1 year. Okay, that means T from 0 to T equals N is going to be 1 year. T from 0 to T equals 2N is going to be 2 years. So likewise, is N is going to be a number for uh, the determination of the project or the investment's point of view. But the interesting scene here is that inside that capital N, you will see simple M number of interest payments being made for this cash flow that we are going to consider. Carefully look at this again. From T equals 0 to T equals N is going to be your cash flow for a single time period of your discussion. Okay, but instead of we getting one cash flow from T0 to Tn, now intermediately we are going to get more cash flows. In our previous example of we start with 100, then we moved up to 110. So instead of the 10 rupee being paid at T equals N, something equal to that 10 rupee, it might maybe 10 rupee, it may be somewhat lower if you add it up. Okay, something in between is going to be paid for the time period of n. The frequency of those is the denotion by simple m letter here. That means a good example, okay, we'll try to simplify this. A good example would be your simple n is going to be 1 year, simple m is going to be 12. So in that case, what can we discuss? We have the period of 1 year and we are going to get our cash flows 12 times. That means monthly we are going to get cash flows. Okay. So can T be 2n and M be 12? Yes, of course. That means our time period is 2 years. So we are going to get cash flows monthly. And what is going to be the number of total cash flows? That is going to be 24. Why? Because 12 in the year 1 and again 12 in year 2. What's a good example of this kind of cash flow? We can observe, let's say we have taken a loan from a bank. It's a similar pattern of cash flows, isn't that so? So there will be an interest rate, let's say 9%, 10% or 11% in that case. So for that particular interest rate, we are going to pay back the bank at monthly a similar amount, and that is going to occur every month. So that means M is equal to 12 and N can be, if it is a personal loan, maybe 5 years, if it is a housing loan, maybe 10 or 12 years, likewise. So your project or your investment is going to give you cash flows of N number of years, and in between M number of cash flows is going to be received. So the equation that we discussed so far, that is on the future value is equal to present value 1 plus r to the power n, is going to slightly be modified in this way if we want to calculate the future value after n number of time periods. What have we done here? Previously we had future value equals present value 1 plus r to the power n. So the r percent that you received so far in here now is going to be divided by number of times that you are going to receive the cash flow. Let's say R is 12% here. So that means, are you going to get 12% every month? So it can't be the case, is that so? In that case, your 1 rupee or 100 rupee will grow at an exponential rate, and it may be, going to be a few hundreds of rupees after year 1. So that's not going to be the case. Still, you're going to get a return of 12%. So instead of we're going to take R as 12, now the R is going to be 1%. How come? R, that's 12%, shall be divided by 12, that is M number of cash flows will occur for a period of 1 year. Okay. But now the beauty is, previously you can say your future value is 100 multiplied by 1 plus 0.12, that is a 12%, into the power of 1. Okay, that means you're just comparing a period of 1 year. But instead of n being taken as 1, now we have to multiply that by 12. Why? If you look at the previous pattern of cash flows, similarly, now you're going to get 1% after 1 month, then that plus the initial investment for the second month, that plus 10%, sorry, 12% for the third month, so on and so forth. That means now we can't say simple n as 1 anymore. Rather, we have to multiply that by 12 in order to compound this interest that you're going to get by 12 times in order to come to the future value of the cash flow. Let's try to graphically see what I want to highlight here. This is the first option. Let's say this is the second option. We're going to start with 100, grow at a rate of 12%, and we are going to get 105. What's the equation? 100 into 1.12 is going to give me this value of 112. We are happy. We know how that comes. But instead of exactly, we have 12 cash flows here. This is the 12th cash flow. So instead of we are going to take 12% now, this 100 will be coming here, grown at 1%, 101 will come here, grown at rate of 1%. So likewise, we have to get this up until 12 months for us to get the value equal to E. Let's say you're going to have 12%, but instead of one bullet cash flow at the end, you're going to get 12 intermediate cash flows. In that case, your equation is going to be 100, that's your present value, multiplied by 1 plus 12% will be divided by 12 by we have 12 intermediate cash flows. Okay, so instead of now here I have not written 1 here, but assuming time period is 1 year, there is a 1 which I haven't wrote here. So what will happen to that 1? It should be multiplied by number of time periods. Okay, I'll straightforwardly write 12 here. 1 multiplied by 12 is going to be 12 in order to get the value at the end. We'll try to compute that value and see what can we observe. So this is going to be 1 plus 12% divided by 12 is going to be, this is 1%, that means 1.01 to the power of 12. Multiplied by 100 is going to give me a value of 112.68. Let me recalculate and see whether we can see a different number. 1.01 to the power of 12 multiplied by 100, yes, 112.68. If you look at these two numbers and try to do a comparison, what you can see here is that we have received a small portion of 0.68 as extra. Why so? If you carefully look at these initial small numbers of 1 rupee, 1.1 rupee is going to be accumulated and going to give me some additional marginal return compared to this 1 bullet cash payment of 12 rupees that you're going to get here. So that's the difference of the compounding, provided you have intermediate cash flows compared to 1 bullet cash flow. So your equation is going to get improved in a way that you have to multiply the number of cash flows or the number of times by the rate of compounding. Previously it was n, now we have to multiply that by n into m times in order to get the future value. But now the important point is you're not going to get r% anymore. You're going to get r divided by m. That means you have to divide that by number of the number of times that you're going to get interest in order to see the periodical interest. So in this easy example, 12% is the annual interest. So you have to divide that by 12. That means mathematically you are getting 1% every month, and you're going to get that compounded by 12 times for you to compare the value after 1 year. You have to be very careful here. When you look at the questions or the different combinations that you can come up for this compounding, you can see plenty of times that you can confuse R and N by not defining it correctly. Now here easily for a particular time period we have defined M. Now M is going to be greater than 1 in this point of view, but can it be less than 1? Of course there are practical instances also. We're going to get to that section also when we discuss the nominal and effective interest rates. Okay, let's see what we can see here. Okay, so this now we discuss the discussion on future value compounding. Now we learn that for multiple cash flows, you're going to get number of times of interest is going to add up to your initial cash flow, and eventually your value, the future value, is going to be higher and higher. Okay. In a practical instance, we can see the nominal and effective interest rates can be derived from these equations that we discussed a moment ago. Okay. Now, this is very evident in banking business. So many deposits receive interest payments such as monthly, semi-annually, could be quarterly, and many different time intervals being defined. So similarly, deposits, loans can also receive payments on these frequencies also. So both sides can be obviously evident. So due to the effect of compounding, the effective interest rate, in many instances will be defined annual effective rate. Okay, that means the effective rate that you are going to get for a investment, provided you are going to equate that to a time period of 1 year, is the term annual effective rate stands for. Okay, so due to the effect of compounding, AER, or the annual effective rate, is going to get a higher value compared to the nominal interest rate if you get for a smaller time period. Okay, so given m number of periods for a year. Okay, so be careful here. Now m is a number greater than 1, obviously. Because why? We are going to observe, let's say, a monthly or a quarterly, semi-annual kind of a cash flow first. Then we will discuss the opposite side, don't worry. So given m number of periods for a year, AER could be calculated from the equation given below. So the point we want to stress upon here is that now the rate which is going to be equal to annual effective term is going to be somewhat higher than the nominal rate, or the nominal value will be the value that you will see on the face value of your investment. A good example would be, let's say, for 3 months time period, you're going to get an interest rate of let's say 8.5%, a good example. So what will happen to your investment after 3 years? Your investment is going to be over. So you have received 8.5%. So what's the value or the return from return percentage point of view if you want to compare that with different investments? So in investment world, the equating or the comparison base will be very much comparable if we all discuss everything on annual equivalent rates. Okay, let's say we have a rate of 8.5 for a period of 3 months. Now that 3 months will have to be extended for another 3 times of 3 months. That means 0 to 3, your investment is over. That's fine. But that investment notionally will have to take from 3 to 6, 6 to 9, and 9 to 12. And then that particular rate that you're going to get will be the annual effective rate or annual equivalent rate, AER. Now the beauty is your investment is over after 3 months, but you're going to assume that you continue with this pattern of cash flows till 1 year. Have you, in real terms, have you absolutely done this? No, you have not done this. But why do we do this? Because we need to have a individual comparison base. So the previous example shows you, if you write this future value, present value in this particular form, 1 plus r divided by m multiplied by that is m for m number of intermediate time periods and n for your whole number. If you take the same instance, what you see here is that you're going to get 1 year, n equal to 1. Now simple n in this equation is gone. N is equal to 1 year. Why? We are going to compare the annual effective rates. You have the 1 plus r divided by m is the number of time periods. So the 3 months example is going to be 4 here, because you're going to get 4 particular time periods if you are looking at a comparison of a 3-month time period for a period of 1 year, 12 months, 3 months, 3 months, 3 months, 3 months. So 0 to 3, 3 to 6, 6 to 9, and 9 to 12, 4 instances. So the nominal rate of 8.5 shall be divided by 4 number of interest payments and will be multiplied by 4 in order to denote the number of interest payment period for year. So effectively what we have done here is that we have equated from one aspect 1 plus r, that's the annual effective rate, and it should be equal to 1 plus whatever we are going to discuss here as the other side. Okay, now then obviously what will happen is that annual effective or annual equivalent rate is going to be the value that you're going to compute by this 1 plus this entire equation minus 1 in order to compare the annual effective rate. Let me just show you mathematically how we can discuss that also for you to get a clear understanding. Some of these equations, obviously, you don't have to by heart. Rather, you can always argue in a sensible way just by using the simple equation of present value and future value and try to come up with a derived equation in order to compare. Okay. Now on one side, we're going to have a period of 1 year at r%. And on the other side, let's say this is 4, but you can say m number of times. M number of times you're getting cash flows. Okay. Now if you have the same percentage of, let's say, r%, if you have m number of times of cash flows, we learned so far future value is equal to present value 1 plus r divided by n multiplied by n into n. Now this n, I'm going to define this as 1 year. Okay. Now this n, since it is 1 year, will be equal to 1. So that means we can write that 1 off. So eventually we will be left with 1 plus r to the power n. Okay. So here, if I write the equation for future value is going to be equal to present value 1 plus r to the power n. Okay. Now, if we are going to discuss this point and try to calculate the annual effective rate, okay, what we will be eventually doing is that these two values have to be equal to one another. So then this n, since it is 1 year, it is going to be 1, it is gone. So we have on one aspect present value 1 plus r to the power 1. Here this is the angle. So obviously what will happen is that this portion is going to be present value, sorry, no, no. Yeah, so this particular future value is going to be whatever you are going to calculate, that is this value that is coming from the PV into 1 plus R. That means the annual effective rate plus 1 PV. Okay, so that means on the other side also we can say this is M. What do we have here? We have PV, this is R%. So instead of R, now I'm going to call that as AER, because we are going to equate these two sides and try to calculate whatever we are going to calculate for this R in these terms. So instead of R% here, in order to make it very clear, let me put AER. So that means this side is going to give me the equivalent of what we are getting from this R%. Let's say this AER is going to, so obviously bear in mind that this R, this simple R and this simple R is not going to be equal. So that's why I changed this simple R to AER. So AER, let's say you're going to get 11.5. This R is going to be a different number, maybe 11% or maybe 10.9%. So 1 plus AER that you see here, now this portion is going to be equal to this portion by both are in FV terms. That means this is the value that you're going to get from this equation, and this is the value you're going to get from this equation. So both should be equal for us to compare this simple R to the AER. Okay. So instead of this FP on one aspect, I've taken this equation of PV AER. When we have two PVs, we can cross it off. That means AER. That means this equivalent to this R. These are the two bases that we're going to compare here. This AER plus 1 is going to be 1 plus R2 divided by M plus M to the power M. I'm sorry. So lastly, we are going to get the equation of AER, that is 1 plus R to the R divided by M to the power M minus 1. And that is how we have derived here the equation to be so. Now this R, I call it as the nominal rate, or in this sense, your investment is over after smaller time period. Now this is the R you are going to get. However, we are assuming that this R will last for the next number of time periods, M number of times, and will give you a return. But that is a hypothetical assumption. But your R is over before 1 year time period. Now that, let's say that 8.5 that you're going to get for this time period, that percentage you cannot compare with the other investments. Why? Because your timing is somewhat different. Can we discuss another one? Let's say this R, another instance. Now this is 1 year. What if you can see a time interval of, let's say, 14 months? Obviously, the same math could be used. Your 14-month interest, you're going to get after 14 months, one interest payment, okay? Not intermediate. After 14 months, 100 after 14 months, let's say 114. Now, this cash flow that you have received is more than 12 months, more than 1 year. Obviously, we have a problem. We can't easily compare this at 14 with whatever you are going to get after 1 year. This is also the same principle of M and R could be used here also. We'll see a couple of worked examples in the slides. Okay. So bear in mind this nominal rate, or the rate that you see here on the right hand side is whatever the rate that you are going to get for your irregular time period. That should be, it could be less than 1 year, it could be more than 1 year also. Okay. Look at this table. Now this is a typical type of interest schedule that you can see in a bank's website. I've taken this from a bank website. It's not a very recent one, it's somewhat older. What do they say? You have different time periods of 1 month, 3 months, 6 months, 12 months, and 24 months. And broadly, we are looking at two different options. Option on the middle is where you're going to get interest on maturity, and the right hand side, interest paid on monthly. Now that's a good example of this compounding we discussed a moment ago. That is, you're going to get some intermediate cash flows. Okay, right. Look at the values in percentages. Those are the nominal interest rates that you would see in our previous equation. The nominal interest rates are 5% for 1 month, 8.5% 3 months, 10.5% 6 months, 10.25% 12 months, 11.5% 12 months. Okay. In the brackets, words in the brackets, AER, annual effective rate or annual equivalent rate, is the one that we have calculated based on the equation that we done so far. Okay. Look at the AER value of 5.12. What does it mean? That means this 0.05% shall be divided by 12. That means this 5% that you're going to get on monthly shall be reinvested for another 11 times, total of 12 times. Multiply that by, take that into the 12th power, will be the value, minus 1 obviously, will be the value of 5.12. That means your investment is over after 1 year. That's okay, that's fine. But this is equivalent to, you keep the money for a period of 1 year at a rate of 5.12. I repeat, your investment is over after 1 year, but this is equal to your investment being kept at a time period of 12 months at 12 different instances, 12 different investment on a monthly basis. Look at one more example. Check this out. Now this is a good example. 24 months. Okay. Your nominal rate is 11.5%. What does that mean? After, now look at this header, interest paid at maturity. That means your interest is going to be equal to 11.5% after 12 months. So that means, say you invest 100 rupees, simply you are going to get 111.5 rupees after 24 months. Okay, not 12 months. So the AER equation will be very interesting here. Look at the interest rate, 11.5%. That's fine. That's kept at the position of nominal rate. Now, instead of 12 that you see here, from annual point of view, you see 12 different cash flows. Okay. But from annual point of view, this 24 month is equal to 0.5. You have to get that clear. Okay. 24 month means you have 0.5 compared to 1 year. This 12 is 12 times of 1 month, that is equal to 1 year. This 24 is more than 12, that means this has to be a fraction. Okay, so your M, or the number of period, this time is going to be 0.5 if you are comparing 24-month investment. That's it. So the M is the number of times, here 12 times, here 0.5 times. So this equation is going to be 11.5 divided by 11.5% divided by 0.5. You have to take the power of 0.5. It is going to give you a value of 10.91. Okay, see, what does this mean? That means this is equal to, you're going to get a 10.91% interest after 1 year. You multiply that by another year and you're going to get a interest rate of 11.5. If you take the calculator, I'm going to add 1.1091 to the power of 2. It's going to give me a return of 11.5. That means you take the first year's interest of 10.91% and multiply that by again another 10.91% will give you a return of 11.1. Look at the 12 months example here. 10.25, 10.25. What can you see here? Interestingly, at 12 months, you don't have an annual equivalent rate. It is going to be the same. The nominal rate and the AER is going to be the same. Isn't that so? Because if you look at this now, if you apply this same to the equation, what you see here is 10.25, 10.25. AER equivalent number of cash flows, it is going to be 1. So 10.25 divided by 1. Number of times 1. That means 1 time. AER equation is going to be equal to the nominal interest or the simple interest rate of 10.25. Now look into this equation. 12 months, similarly, 12 months, but instead of we are going to get interest at maturity, instead of that, we are going to get under this option interest on monthly basis. So now that's the difference. If you're going to get monthly interest rate at 10.25, here also, this 10.25 here also, it is going to obviously give you a much more higher AER. So obviously what the bank has done here is that instead of 10.25, it has designed a somewhat marginal rate of 9.75. And if you look at the AER, sorry, it is going to give you a almost similar or a marginally low AER compared to this 12 month. What's the equation? Same equation. This is the rate, 0.0975, 9.75%. Okay, divide by 12. Why? 12 monthly interest payments. Simple. Unlike these instances, you don't have to determine whether you're going to get a more than period or less than period. This is 12 and 12. Same. You can compare. Number of times is also 12. So obviously, this is going to give you an answer of 10.25. If you look at this AERs of 10.25 and 10.20, this is pretty much close by. So bank has make sure that provided you got your interest at maturity or monthly, is both going to give you a similar kind of a return. How they have done it is by giving you a marginal less return of monthly on a nominal basis compared to the maturity basis. Okay, so this is a good example of nominal and effective interest rate being computed. This is the equation for AER computation. We can see a lot of MCQ style questions in your exam paper also. No worry, we'll look into that in the next week. Right. Now next, we are moving ahead with our discussion on different styles of cash flows that you can observe. So this is another form. We call this as annuities. Annuity is a series of cash flows. Now, obviously, this cash flow has to be equal or uh, same. Okay, it's a series of equal cash flows which is going to incur for a given time period. Let's say 5 years, 10 years, 15 years, so on and so forth. A good example would be your loan interest payment. Provided you have taken a loan, you can see an equal amount being deducted by your point of view to the bank. For let's say 10 years monthly, that means 120 time periods. Okay, equal cash flows, 120 cash periods, time periods, right? If this time period extend till infinity, now provided this is 10 years, 15 years, for a finite number of years, it's over. That means it's a form of annuity. It's a financial term that we define it. But provided this time period is infinite, then this term of annuity we can reword it as perpetuity. It suggested that it does not have an end to the cash flow. That means it's very rare to find these kind of cash flows, but certain jargon such as insurance and leasing, you may find this kind of cash flows, but not very common in practice. Uh, in our previous example, we discussed that equal amount of cash flows, 120 periods for a 10-year period. But if you see a cash flow which does not have an end, we can reword the term annuity into the term of perpetuity, right? So now, still we are under the area of future value. For a future, now previously what we have learned, future value is equal to present value plus 1 plus r to the power n. Provided you have intermediate cash flows, we learn another equation. It is going to be future value is equal to present value 1 plus r divided by n for the number of time periods. That capital N, number of years, kind of simple N will be multiplied by n. That's what we have learned so far. So mathematically, uh, we can discuss this under the time series jargon, where when you have a series of cash flows like this, look at this example. The first cash flow is going to be incurred after year 1, 1000. Second cash flow after year 2. Third cash flow, 1000, so on and so forth. Last cash flow at year 5. Okay. So what has happened here is that these individual cash flows is going to be reinvested for a number of years. If you look at this equation of what you see here, 1000 multiplied by 1.04, number of time periods 4. That is going to give me 1215 kind of a value. Similarly, this one 3 cash flows, this one 2, this one 1, and the last one there's no absolute value. That means right now, that means 1000 itself. Okay, so the sum of these $5,000 cash flows is going to give me a value of 5525. So this is one method where you can find the future value or the value after 5 years, provided you see $1,000 of payments in equal terms for 5 years. Mathematically, what we have done is this 1 plus, now if you look at this carefully, this 1.05, this is nothing but 1 plus r. So if you write this, this is going to be equal to 1000 multiplied by 1 plus r to the power n, and n is equal to 4, 3, 2, and 1 and 0 at these individual points. So interestingly, you can apply this equation of 1 plus r to the power n minus 1 divided by r, that particular term that is shown here, multiplied by this 1000 rupees is going to give you the future value mathematically. So both are equal. If you look at this example of 1000 rupees, if I take my calculator, 1000 is going to be 1000. 1 plus r in this example is going to be 0.5. Okay, so this is going to be 1.05 to the power of 5, n is equal to, sorry, 4. What we see is 4 number of reinvestments, okay, minus 1, divide by 0.5 multiplied by 1000 is going to give me a value of 5525. I repeat the calculation, 1.05, give me a second, 0.05, yeah, multiplied by 1000, yes, that's correct, 5525. Yeah, so this is one form of future value calculation for an annuity. Either, if you forget this equation, don't worry, you can apply the simple timeline and get the future value in a similar way. So this is one particular style we call the payment in arrears. That means payment or the cash flow is going to occur after 1 year time period. But what if you have the payment or this annuity in advance? That means for this particular year one, this 1000 is going to compensate. But what if we move this 1000 here? That means this set of cash flows, this 1 year's cash flow of 1000 is going to come for 0. The second year is come to 1, third year to 2, fourth year to 3, and fifth year to 4. So this is the last point. Okay. In this instance, nothing happens miraculously. What all happens here is that this entire portion remains same. Number of periods will be 4 now instead of 5 here. But only difference is now you have one more A to be computed right now. That means this equation, instead of A, you can see A is equal to A plus A into R. That means this last cash flow will be also compensated. So if you would recall that this particular form of equation is going to give you the future value for annuities in payment in normal terms. In payment in advance term, all what you have to recall is that there's going to be 1 plus R to the annuity, provided that your payment or the equal amount is going to be paid in advance for a particular time period. So these are the two forms that we can discuss an annuity. Okay, I repeat, for annuity computations, either you can use the simple future value, present value for individual cash flows and get the summation that will give you the future value. Also, you can apply the formula. So the exam point of view, I haven't seen much specification as to use a particular method. Rather, all what you have to do is compare the future value and a present value for a given sum. Okay. Extending this discussion of annuity into perpetuity, provided that your time period, that n is going to be equal to infinity, the future value is also going to be a value of infinity. That means this R, this interest rate of, in this example, 5%, don't worry, R is not going to be impacted by this. But n, instead of a finite number of 5 and 4 in these examples of arrears and advance, this n is going to go to infinity. That means this 1 plus n, sorry, 1 plus R, this value is also going to be a infinity equivalent value. So minus 1 marginal diminution, divide by this R, this also, this remain constant, will get a value of future value of a infinity value. So for a perpetuity, we don't really discuss the future value. But for annuity, for a defined time period, we can discuss the future value either by a manual method or a equation method. Now, having discussed everything on the future value, in slide 3 or 4, what we have discussed is the present value. Provided that you have given a value for a future term and you want to calculate the value in present terms, the present value is nothing but the opposite of the future value equation. So if you know the future value, you have to divide that by 1 plus r to the power n. That means, let's say a classic example of 10% 1 year, and you know the future value of, let's say, 130. Okay, 130, 10% 1 year means 130 you have to divide by 1.1. That means 130 after 1 year is going to be equal to 118.18 in current terms. So if you take out this future value FV part and try to see what remains, it has a remainder of 1 divided by 1 plus r to the power n. Now friends, we call that 1 divided by 1 plus r to the power n as the discount factor. So that means whatever you put on the top of the equation will be discounted by this particular factor. Now in some certain exams also, these discount factor tables should be also available in the last page of your exam paper. How come one can calculate these discount factors in advance, but I mean, can't they be different? But if you carefully look at the R's and N's in practical sense, all what we see is R can be, let's say, 1%, 2%, 3% kind of a complete number. N is again also going to be 1 year, 2 year, 3 year, 20 year likewise. So if you take R into one axis and N into the other axis, you can plot all these numbers in different combinations and come up with a nice table. We sometimes call that as a discount factor table. Okay. A good example would be, let's say, 10% 1 year. If I calculate this factor, I'm going to get an answer of 1 divided by 1.1. Is going to be 0.909090. So in mathematical term, we call it as 0.9091. 1%, sorry, 10%, let's say for a period of 2 years, I'm going to get a value of 1 divided by 1 plus 0.1, that is 1.1 to the power of 2, 0.8264. 3 year, 1.1, sorry, 1 divided by 1.1 to the power 3, 0.7513. Now these numbers are the discount factors for a particular percentage for a period of 1, 2, 3, 4, and 5. Okay. Now there will be a lot of interesting sums to discuss under the present value and the net present value. So bear in mind that there's nothing confusing here. All what we have is the same future value equation being converted into present value terms. Why? Now, all these previous instances, we knew that there are going to be some cash flows and we need to find the value at a future date. But now, the jargon is somewhat different. Instead of future, now we know the future cash flows and we want to assess those cash flows in current terms. And for that, we are going to use the discount factor. Okay, that means, let's say you're facing a sum of a project. You may have different cash flows. What you have to do is you can write the cash flows. If there are adjustments like tax and depreciation, those are all maths and business terms. We do the justice to all these cash flows based on our knowledge, and then we have a net cash flow. Those net cash flows will be multiplied by these discount factors, and then you get the discounted cash flows. And that is the next discussion on the net present value. We'll go there pretty soon. Okay. So nothing new here. Present value, same equation of future value, just that we, instead of the future values in the previous discussions, here we are going to discuss the present values. Same terms, R's and N's, same. Look at this graph. It is also somewhat elaborative on these two variables of time period and different interest rates. Now this axis is your value. Like in our previous graph of $1 being compared, this is $1,000 being compared at different time periods of, let's say these are years of 0, 25, 50, likewise, and these are discount rate or the R. These are, okay. So these are lines of 2%, 3%, 5%, and 7% being applied to this R that is shown here. Okay, that means this future value of 1,000 should be discounted by 2% for a period of 25, 50, 75. This 1000 discounted at a rate of 3% discount rate by 25, 50, 75, so on and so forth. What we can observe here is that for a given discount rate, let's say for this line shown here, for this given 3%, longer the period, 25, 50, 75, longer the period, your present value is going to be lower. On the other hand, for a given time period, let's say 50, higher the discount rate, that means I am here at 50, higher the discount rate, that means 2, 3, 5, and 7. So this is the highest rate. Higher the discount rate, the present value is going to be lower. So the visual explanation that I want to highlight here is that provided you have the longer time periods and longer time periods and larger discount rates, your present value or the current value is going to be lower. That's fair, isn't that so? In our first example, we discussed for a period of 7 months, 1000 rupees. Let's say 17 months, 77 months. Your value after 77 months, if you are going to compare right now, is going to be very diminished if you're going to compare the same 1000 rupees and 1000 rupees at that time of 77 months. So that is what is shown here. But now the new variable that we brought into our initial discussion is nothing but the R, or the interest rate that we're going to discount these cash flows. Okay. Now previously we discussed something interesting, that is an annuity. That means a set of cash flows that is being nicely laid out for a defined time period. Perpetuity is an extension, we'll come to that in a little while. For a nice defined time period of annuities, we discussed that, okay, if the same cash flow being repeated over and over again, we could calculate future value easily by taking 1 plus r to the power n minus 1 divided by r. Okay. So the same form, it's again coming from the mathematics on time series cash flows. So the same series of A's, now instead of we are going to look for a future value, now we are going to discuss for a present value. Same series of those cash flows can be then discounted to current day in order to calculate the value on present value terms. So this is the fundamental argument that we are going to take for our discussion on net present value. So because of that, let me just try to explain you what my argument is. Okay. Now here, excuse me for that. Now here what we see is, this is the present value, so this is the current day, current terms. What we are going to see is same cash flow of A, we go until A n times. This is 0, 1, 2. Let's say this is n minus 1 in that case, and n times. This A from present value terms, come back. So I have these years of 1, 2, n minus 1 up until year n. Okay. So this cash flows of A's shall be discounted in this case for the present term. What's the equation that we are going to use here? The only or simple equation that we will be applying throughout this is nothing but the future value is equal to present value 1 plus r to the power n. I'm going to take the present value. So if the present value is what I want for this cash flow, I have to take the value of the future These are the future values at year 1, year 2, year n minus 1, upper year n. Okay. So this value should be, I know this future value is the A, and the present value is A divided by 1 plus r to the power n. I'm going to define this by r percent. Okay. So this is in that case going to be A divided by 1 plus r to the power 1. Why 1 here? This is going to be A divided by 1 plus r to the power 2. 2 years. Similarly, this is going to give me a value of A divided by 1 plus r to the power n minus 1. Last one, A divided by 1 plus r to the power n. Okay. So either, provided that you're given 3 years or 4 years, you can forget this entire equation dilemma and apply your simple knowledge on the present value and future value and calculate the summation of these values and get the idea for the get the present value idea for the annuity. The other equation is you can take the A from here common, then you have 1 plus r here, 1 plus r to the power 2 here. Likewise, then you are adding up a mathematical time series 1 plus r to the power n. If you went on this form, there's a universal equation where you can add up these values and get the final value. So that equation is the equation that I've given in the slides. That is going to be 1 minus 1 plus r to the power minus n instead of plus n in the previous equation divided by r. Do we see some commonality here with the previous equation? Previous one, we can, now this is the present value. If you look at the future value equation, in your previous slides, for a same annuity, what we have taken here is 1 plus r to the power n minus 1 divided by r. Isn't that so? So if you could recall this one, this form 1 plus r to the power n minus 1 divided by r, the same form, marginal difference. So instead of 1 plus r to the power n minus 1, here we have 1 minus 1 plus r to the power negative n. Provided if you want to be a little faster in this computation and you want to calculate an annuity for a present value, let's say 20 years, can you do this and add up 20 years at the exam or in practical sense? Somewhat difficult. So you can use this equation. So the remainder, the A and these other factors will remain same. So simply what we have done here is that provided you have a same cash flow of A, that A multiplied by 1 minus 1 plus r to the power negative n divided by r is going to give you the present value. That is the part, that is a theory part I want to highlight here. This is in case where you have a annuity, that's a equal cash flow running for a longer time period. So the both methods that we can discuss here, the payment in arrears and payment in advance, the only difference here is that similar to our previous case, here we have one additional A, that is the first year's cash flow paid now. Okay, first year's cash flow paid now is going to make nothing but a small difference here. Instead of A divided by 1 plus r here, now we have A. So the rest of the cash flows will be similar in this case. So in that case, if you want to calculate the present value in equation terms, you can take that A aside. Okay, and instead of n, now we have n minus 1 times of cash flows. Okay, so that means from equation point of view, if you want to argue the present value of payment in advance method, I have not even given here because you can argue. I mean, too much equations can make your life difficult sometimes. Okay, so the arrears equation, you will take it as it is. Then we are talking about the present value. So if anything comes into present terms, so this a term that comes here is going to be t equals 0, or right now, here 0 right now. So it is going to be added to the present value. So this equation will be converted to a plus. Okay, a plus. This entire section will be repeated. So instead of this n, now we have n minus number of cash flows. Isn't that so? So this rest of the part, if you look at this a divided by 1 plus r, a divided by 1 plus r to the power 2, similarly it goes up to n minus 1. Okay? That's what is repeated here. So if you have a cash flow like this up until n, your equation is going to be something like this. So instead, if you have a cash flow like this up until n minus 1 number of years, so instead of this simple n, nicely put a n minus 1 and you have the equation. So this is enough for you to keep in mind, provided you have a longer cash period like 17 years or 20 years at the examination for you to calculate the annuity present value. Okay. So the difference, or the nice difference that we can come from this discussion is nothing but the conversion of what we have just learned, that is the present value of an annuity, what it will happen if we want to discuss for a perpetuity. So that means now previously in the future value argument, we discuss higher the n, higher the r, obviously. Sorry, for a given r, higher the n. N is the only thing that is going to increase. Is that so? So for a perpetuity, if it goes up until from 0 to infinity, we say we don't really discuss the future value. But something magical happens here. Okay, I'll erase these things, and I'll only write the form of the equation for us to discuss. Okay, what we learned just now is that present value of an annuity is going to be annuity multiplied by 1 minus 1 plus r to the power negative 1, sorry, negative n divided by r. Okay. So this is the beauty. R, we don't really worry. It's a number given in this discussion. So what happens is that when n goes into infinity, negative n is going to be 0. If I rewrite this part slowly, mathematically, what does it mean here is that, forget about these parts, I'm just going to elaborate what I can see here. Okay, this is 1 minus negative n means 1 divided by 1 plus r to the power n. This is same as this. This is negative n, this is positive n. Good example, 2 to the power negative 2 is equal to 1 divided by 2 to the power 2. Same thing, I'm rewriting here. So when this n become larger, n goes to infinity, this is a much more larger value. So 1 divided by a larger number, this is going to be equal to 0. Okay. So that's why I argued when n is going to be an infinity or perpetuity, this is going to be close to 0. And obviously, then what we can say here, this term becomes 0, 0. This is the remainder. That is why I have given in the last point, for a perpetuity, forget this negative part of the equation and you will be left with annuity divided by interest rate will be the present value for a perpetuity in that case. Okay. Right. We discussed plenty of things. We discussed present value, sorry, future value of normal cash flows, compounding, different types of interests, simple and compounding interest. Then we discuss on the perpetuities, annuities. We discuss present value of both these perpetuities and annuities. So those are the all different types of ingredients that we can see in a cash flow pattern. It could be an investment, it could be a treasury bond, treasury bill investment, it could be a project cash flow, it could be a loan, anything that may have regular cash flows, that may have a similar cash flow like capital A, could be anything. But these are the ingredients. If we boil down everything back to the basics, we are only left with one equation, that is a future value equals to present value 1 plus r to the power n. Students, that's the only equation that all brings to this point. Okay, all these complex equations like 1 plus r to the power n minus 1 or this negative form, those are all mathematical advancements of time series analysis, where you can make your life easy when you have to do manual calculations for 20-30 different numbers. Okay, now we are moving to the last part of our discussion, that is the net present value, or the core of this subject area, where you can see plenty of discussions at the examination. So this NPV concept, the net present value concept, is nothing but the same thing that we discuss on the present value. Provided you have different cash flows in the future time period, you have to compare that on a today's point of view in order to make a decision. So the project finance, the capital budgeting, suggesting that for decision making, if you know the future cash flow that is going to occur in a time period ahead, you have to discount everything for a day like today and take the present value. When you have the net impact of all these positives and negative cash flows, we convert everything into net present value. That is the difference between your cash flows that is going to incur at different points with the initial investment. Okay, we'll discuss the theory a little later. Okay, we'll discuss it now, and then I'll go to the board and show you what I meant by these different cash flows. Okay, in simple NPV terms, capital budgeting attempts to invest the funds available on efficiently in the long term, expecting a net benefit to the company. Provided that you are looking at 2-3 years kind of investments, you will always have to make sure that you're going to make a net positive impact to the company. Okay, bearing in mind, NPV is the difference between all future cash flows to the initial investment. Okay, if I go to the board, I should be able to show you what I meant here. Now say, in typical project terms, typical investments, what we can see here is that there is a big initial cash outlay at the beginning of any project. Let's say, year 0, I have a big outflow, 10,000 rupees. Gone. Let's say I got a machine, put up a house and got a small machine of some manufacturing, and then the project goes on. Okay. Then after year 1, 2, 3, and 4, let's say my project is over after year 4. First year I'm going to get 2,000 rupees. This is 12,000 rupees. This is 20,000 rupees. Last year project is closing 17,000 rupees, and I'm going to sell this machine also. Now these different cash flows is going to occur in future time periods. How do we know this? This could be estimated by cost accountants, by analysts, by financial evaluators. Anyone could decide these cash flows. Now this kind of a cash flow suggested that these all could be converted into present value terms. All these. We learned so far these values will be marginally lower depending on the number of time period that you are going to discuss. Let's say hypothetically this is equal to 1,700, this is equal to 10,000, this is equal to 15,000, and some values. I'm going to just take this present value, forget this part. Present value of these will be, let's say, 37,000. This section. This versus this will be my net present value. NPV suggested that I take out the initial investment. Why I can take it out easily? Because it occurs in year 0. Bear in mind, year 0. Okay. So that means I have a net advantage of 27,000 from today's point of view, provided my project was like this. Okay. Bear in mind, the equation that we discussed in this slide set, NPV equal to present value of all cash flows minus initial investment. Bear in mind that in real term, in actual terms rather, uh, your initial cash outlay may not be the only cash outlay. Maybe there's another 2,000 here. So what will happen? That's okay. So you can net it up on one aspect. Say this is 18,000, or you can take the NPVs of this and take the NPV of this value. It's a negative number. Add everything up again. A new fresh NPV is going to be received. So in practical sense, don't really get uh, carried away that every investment is going to be you have initial cash outlay and all positive cash flows. There can be negative cash flows also. Okay, so forget about the positivity or the negativity of the cash flows. All what we do is we do the present value computation. So based on the positivity or negativity, your present value will have a different impact. And why do we take these separately and deduct the value here? Is that it is on year 0. If you have a positive cash flow of, let's say, 2,000 here, fine, you have to add this up also. You can either net it up, or you can say this is 27,000 plus this 2,000 is going to be 29,000. Likewise. So this concept of NPV is going to suggest me nothing but a very simple theory on what we learned so far on the present value, which says that if you have a set of cash flows which goes from now to, let's say, a finite number of time periods, you discount everything into today's term minus the initial investment is going to give me the net present value of this particular set of cash flows. Very importantly, if there are any adjustments like tax, a good example, you have to take the tax effect after when we want to get the cash flow. That's why in this universal form of equation, I have said the CFT, the CF stands for cash flow, T means at time T. This has to be after tax or any other adjustment that is given in any sum. Okay, right. So the universal thing is that for one could argue, why are we going to apply the same interest rate? Can't we apply different interest? Okay, those are all possible in the NPV jargon, but provided that we are at the very fundamental level and discussing these factors on the NPV, we can assume that the R rate is going to be constant throughout the lifetime of the project. Okay, bear with me for another 5 to 7 minutes. There's very minor theory part to be discussed. We'll try to finish it off so that we can freshly start with the NPV sums on the next week. Okay. What we discussed in steps form is given here. The steps involved in any NPV computation is first, easily identify all cash inflows and outflows, like the class example we discussed. Determination of a suitable discount factor. A lot of questions they will directly give you. This company will take 10% as the discount factor or the required return. Required return is also another term. Let's say one form is that you will give discount rate is 10%, or the required rate for the company is 10%. So either of these terms should ring a bell and say, okay, that should be my simple R. Third step is all present values using these above discount rates, using those discount factors that we discussed, 1 divided by 1 plus R to the power n, you can discount those cash flows to the today's term. Take the summation or the present value. And when you take the summation, be careful. You have negative cash, positive cash flows, negative cash flows. The summation should net it out. That's why we call it the net present value. Once we have everything on net present value terms, once we have everything on today's term, you have a nice ground to evaluate anything. But in a case where you will be given this example, this class example, and you come up with a positive NPV of 27,000, there's nothing more to evaluate. It's a positive number. That's what I've given here in this decision making process also. If it is a positive number, it's an independent project, you can see it. That means this cash flow set is going to derive me a positive value to the company. Provided you have multiple projects, let's say 3 different NPV numbers. First number 10,000, second number 15,000, third number 27,000. You have to take the 27,000 provided that you have the opportunity. And there are a lot of interesting questions that we can discuss on next week. Sometimes certain things can be rationing the capital. That means you have to ration the capital among a couple of projects. Those are practical instances. You can invest in one project, you can invest in second project, provided you have some cash left. So those are all practical common sense instances, provided you have your initial investment of, let's say, 100,000. First project wants 50,000, second project 60,000, third project 40,000. Now, obviously, you can understand that 100,000 is less than the summation of all three. You can't do all three. We can calculate NPV for different projects. We can look into the maximum generation. If you can ration the capital and allocate a percentage of your capital to these projects, that could be the optimal way. But if you can't ration your capital, maybe you can take project 1 and 2 with the best NPVs. So those are all different scenarios that we can see on the next week questions. So bear in mind, NPV is nothing but your present value equation being used to different cash flows at different times using one common discount rate or the interest rate. Last but not least, one additional factor that I want to touch upon this lecture area is the area on internal rate of return. So this, if you look carefully, look at the exam papers, this is merely not being practiced or not being questioned much. But when you look at a couple of questions, I thought of putting this up also. This is nothing but if you apply this project cash flows at different rates. Now, in this example, we applied it, let's say 10%. We got a number. What could be the different factor? The only difference factor is the R, the interest rate. Cash flows are constant. You can't change it. Times are constant. You can't change that also. But R, if you have a different number to R, obviously you will have a different number to the NPV. Okay. So there is a point. I'll stop the discussion with this point. There is a point. There's a sweet point where you can calculate your project to have a break-even kind of a point. Let's say these are discounted at 10%. I'm going to write R here, interest rate at 10%. I got a positive number, 27,000. This axis is NPV. Okay. If I lower the interest rate, I will have a higher NPV. If I turn up the interest rate, the R, my discount values is going to be lower and lower and lower. Let's say a good example is I take it up to 11%, my present value will be close to 22,000. Okay? These are all hypothetical examples. Now, likewise, I move on to a point of, let's say, 17%, where that is the sweet spot. Beyond 17%, if I apply this rate to these cash flows, I will see a negative NPV. I don't like that project. But this point, 17%, is the rate that we are going to define as IRR, internal rate of return. In practice, obviously you can plug all these cash flows to a nice Excel sheet, and there are equations in Excel also saying IRR where you can easily compute. But in practice, I'll show you how you do it. Provided we have time, we'll try to do some NPV sums and we'll do a new IRR sum for your knowledge. How do you calculate this? Is merely by in practice. Now you can't do it 30 or 40 different times and find the exact number. Rather, let's say you calculate this set of cash flows at 15% and then you come up with a number of, let's say, 12,000 as NPV. Then you calculate this at 20%. In our previous example, obviously, we know that this is going to be a negative NPV. This is NPV axis. This is my R or interest rate. Now, when we have this kind of a relationship, we can have a linear approximation and say approximately at 17%, or depending on your distance of these numbers, you will maybe get an exact number or maybe a closer number. Depending on these 2 points of NPVs, you can mathematically argue, okay, 0 has to be a point like this. What you do here is nothing but the small equation. Let's say this is R. So you can use the basic trigonometry here. So you have R minus 15. This should be equal to, sorry, this ratio 20 minus R should be equal to this height of 12,000 to this height of 3,000. So this kind of a relationship could be used to calculate the rate R or the IRR in this point. Don't worry, not being tested much, but for knowledge term, we need to discuss IRR also for us to get the perfect coverage of the theory on NPV. So to sum up, IRR is nothing but the point or the R where your NPV is going to be 0. So IRR point of view, if you have been invited to make a decision, you have to always look at the required rate of return for this company. Let's say my company or my investment, I need 11%. And this project's IRR is going to give me a higher number. In that case, we can consider that investment. But provided you have a break-even IRR of a lesser number to my required rate, you can not consider that investment. That's the decision rule of the IRR. Provided we have some time next week after the discussion on the NPV sum, we'll try to do a question so that you will understand the practicality of this number as well. Okay. Thank you for the extra couple of minutes. To quickly sum up, we discussed on the future value, compounding, nominal and effective interest rates, and then we came to annuities and perpetuities. We discussed the annuities and perpetuities, both present value and future value, and then we came to this nice concept of net present value. We don't have to spend much time on net present value because it's an extension of the present value. Multiple different cash flows being tested in different, being located in different time periods. We can discount them, calculate the net present value. The extension of net present value is, if you change the R, you will have different net present values. And there's one particular R where you are going to marginally get an NPV of 0. So from IRR and from NPV, there are two different decision rules for a company. Depending on the number, you can either accept or reject the project. Thank you for the time. We will meet you again with the next week's discussion on the questions, past paper questions on the NPV for the past couple of years. Okay, thank you.